Yeah, hello, good day to all. So today I'm going to discuss a few concepts about the Unit 1 of Mathematics 2 as per JNTU Kakinada syllabus. The syllabus is advised by the JNTU Kakinada under the regulation of R20, and in this one, this is the first unit. So in the first unit, we are going to discuss now. So in this, the title is Solving System of Linear Equations and Eigenvalues, Eigenvectors. Earlier, up to the system of linear equations one unit, but it is in revision. Eigenvalues, eigenvectors are attached to this in the first unit. And it's to that here earlier scenario, electrical circuit concept was there, but it was removed, I think so. So it's not clearly specified. So we are in place of the electrical circuits. We are going to discuss here eigenvalues and eigenvectors. And this, the major concepts that which we are going to study is actually it is given here directly a rank of a matrix. So but if you go rank of the matrix, for some people they might not be have the basic concepts quite clear. So that's the reason. First, what we'll study is here the topics which I'm going to discuss into this is, first we may discuss about what is a matrix and how many types of the matrix, types of matrices, and what type of the operations that we are going to perform, operations that we are going to perform, and then how to compute the determinant. Then only I may start a rank of a matrix. These are the basic prerequisites. First we'll discuss this, then we may come to this one. So this will be studied under the linear algebra. The main content of this one is a linear algebra. Under the linear algebra, we are studying this matrices. Now, and this under this, we are going to study these are the topics. What exactly this is? Linear algebra, where exactly we are going to use? It is a fairly extensive subject that covers vectors. We thought that vectors is different. No, vectors also a part and parcel of the matrices. Vectors and matrices, determinants, system of linear equations. Here we are not going to study vector spaces and linear transformations. Actually, that is abstract concepts. So we are not, as per syllabus, it's not specified. So I'm avoiding this. Actually, these are the topics under the linear algebra. In the linear algebra, we are precisely restricting to only matrices. Then eigenvalue problems and other topics we are going to discuss now. Now, matrix is nothing but arrangement of the elements in a rectangular fashion or regular arrangement of numbers. Regular arrangement of, best example, we can see that we are arranging switches in a switchboard, or we are arranging the people in a classroom in a regular order during the examination times and all. So these are the common matrices per row. So in that one, the vertical arrangements are known as columns, and horizontal arrangements are known as rows. And the matrices, as I told, the matrices addition and scalar multiplication we are going to discuss now. So these are the best examples. So this is these are known as rows. Row 1, row 2. This is a row 1, this is a row 2, this is a column 1, This is a column 2. This is a column 3. Similarly here, this indicates, if I denote this suffix, the last suffix would be the order of the matrix. The meaning of this one is, this is number of rows of a matrix. This would be the number of columns of a matrix. Here it consists of only one row. So this is known as a row matrix. It consists of only columns, so this is known as a column matrix. The same we are going to study this as later classes as a vector. Just have an eye on that. I'm not going to focus much more on that. Now, a matrix is this regular arrangement of numbers or functions which will enclose in the brackets. Now, let me clear the annotations. So then here, matrices. The matrices are the numbers. Just a minute. So here, a regular arrangement of the elements is like that. Now, columns and rows that we discussed already. The matrix is just a single row, and these are the details of that. Row vector and column vector. Generally, we denote the column matrices with capital letters only, not with small letters, and the order is denoted by m by n, and it will be read as m by n. Do not read this as m times n. This is m by n only. The way that is known as size of the matrix, order or size of the matrix, which indicates that it consists of m rows and n columns. The best example is here. A is Aij. Aij is the A, J, K or Aij, whatever it might be. So this J represents the element which belongs to the jth row and the kth column. Means if you take any random element, if any random element of the matrix, the meaning of that one is AJK, means the element which belongs to the jth row and the kth column. The matrices of the size are generally we go up to 3 by 3, at most 4 by 4 only, but in industrial purpose or in real world time it will be n by n. Especially these concepts are more utilized in nowadays allied branches of the computer science, artificial intelligence, machine learning, data science. In that one, very rigorously we are going to use this linear algebra concepts. Row, if suppose the size of the matrix means number of rows and number of columns are equal, then it is known as a square matrix. Number of rows equal to number of columns. Here, if number of rows is equals to number of columns, then it is known as a square matrix. And for every matrix we have these two types. The diagonals are, suppose a matrix consists of like this: A1, A2, A3, A4, A5, A6, A7, A8, A9. Means it is a square matrix. This is one diagonal that we have. This is another diagonal that we have. Instead of writing like this, if I write in the proper manner like this, if I write like this, say this. In this one, if you observe carefully that row number is equal to column number, row number is equal to column number if it is n by n. if it is m by m, if I consider row number is equal to column number n1, n2 and so on nn. Row number is equal to column number, then this matrix, this is known as principal diagonal matrix. This is this is known as a principal diagonal of the matrix, and this is also one more diagonal, but in that one we may not get the suffix are same, suffix are different, so this is only a diagonal. That is only a diagonal. This is a principal diagonal of the matrix. Now vectors, just a vector is a matrix with only one row or one column. With only one row or one column. Its entities are called components, and generally it is denoted by bold letters A, B, or simply we generally denote by A bar, B bar, C bar, like that, and so on. And this one vector, this may be A bar is equals -2, 5, 0.8, 0 and 1. A column vector is also, so this column vector, its extension only. Why we are discussing this one is, and eigenvectors. Eigenvectors, we are going to discuss this like this. Eigenvectors are going to be discussed like this. So the same concept you are going to use in eigenvalues and eigenvectors. Then when the two matrices to be equal means unless until their order should be same, first of all, means if A is a 2 by 3 matrix and B should be 2 by 3, first their orders must be same. Then only we may check individual elements. If individual element here, suppose if A 2 by 3, A is not only 2 by 3, any I mean to say that, for example, only I gave A11, A12, A13, A21, A22, A23. This is matrix A. Another matrix B is B11, B12, B13, B21, B22, B23. So first its order is 2 by 3, its order is 2 by 3. Then if it is said to be, if the matrix A and B are said to be equal, unless until Aij equal to Bij for all I comma j. For all I comma j, it must be happens. Then only the matrices are said to be equivalent, or they say equal matrices. So this is what it is given here. Now addition of the matrix. Addition of the matrix is done only when if the orders are same, then corresponding elements we supposed to add, either addition or subtraction, we are going to use the same. A is, suppose it is a 3 by 3, B should be 3 by 3, then only I may either add or subtract. Then I need to add the corresponding or I need to subtract the corresponding. See, the sum of the two matrices A is AJK and BJK, the same size. First of all, the same size means orders should be the same. Then we need to add the corresponding elements. Similarly, for the subtraction also the same. If the orders are different, we cannot do this operation. That then scalar multiplication. So I can multiply a number to a matrix, which means that need to be multiplied with each and every element. So that's what. So if I multiply a arbitrary constant to a matrix, that means that is multiplying to each and every individual element. At the same time, I can take the common also. I can get the common from this. For example, if A is 2, 4, 6, 8, then this can be rewritten here 2 times 1, 2, 3, 4. I may write like this also. Then addition and scalar multiplication, not much big deal, the same. So here, if I add these two, A plus B, then the resultant matrix is equal to the B plus A. This is known as a commutative property or abelian. And A plus B plus C equal to A plus B plus C. Then it is uh, associative property. Associative property. A plus 0. 0 means a null matrix here. A plus O equals to O plus A equals to O plus A equals to A here. Then A plus minus A equals to C. O means minus negative A is the additive inverse of A. Then if all the exist, see this O is 0 matrix. Some people may denote it by the 0 or some people may denote it by the O. Addition and scalar multiplication, that we similarly scalar multiplication of the same. Then matrix multiplication, here we need to be careful. Whereas earlier addition of the matrices is addition and subtraction of the matrix, only the thing is order should be same, but here even the order is same, matrix multiplication may or may not exist. The condition is here we need to hold the number of columns of the first matrix should be equal to the number of rows of the second matrix. Then only the matrix multiplication is possible, otherwise it's not possible. Now let us see that. So the product of AB is possible only in the case of, suppose the order of A is order of A and order of B. We know that order of A is R by B, order of B is in this, see here. Order of A is M by N, A is M by N, order of B is R by P. So the number of columns of first matrix should be equal to the number of rows of the second matrix. Unless until these two are equal, the matrix multiplication does not exist. And moreover, for example, if the matrix multiplication exists, means it doesn't give the guarantee that it is a commutative property. For example, if I see here A is 3 by 2, B is 2 by 4. Obviously, I may get a resultant matrix, let it be C. That is, since these two are equal, so matrix multiplication is possible. That is 3 by 4. Then B times A, if I check, this is 2 by 4, this is 3 by 2. Since these two are not same, so matrix multiplication does not exist. Matrix multiplication does not exist. So resultant matrix here, condition, that what we discussed already. And multiplication. So the multiplication is possible. Every element of the first row is multiplied with every element of the first column. Means A1 times B1 plus A2 times B21, A13 times B13. That resultant matrix is supposed to write like here. So therefore here I can write here C11 is A11 times B11 plus A12 times B21 plus A13 times B31. That is C11. Similarly, A1 first row with the second column, that will be filled here. So here C12 equals to A11 B12 plus A12 B22 plus A13 B32 and so on. That's what the process here. So some example is given. We can see that easily. First row, first column. Here first of all I need to check its order. This order is 3 by 3, this order is 3 by 4. and the resultant order is, by cancelling this, I may get 3 rows, 4 columns I supposed to get here. Actually, this supposed to be done at the intermediate level, but any just brushing, only brushing here. So matrix multiplication is not commuted as we discussed already. Since AB is exist, it doesn't give the guarantee that BA exists. BA may or may not exist. That's what. And arbitrary constants here multiplying. The similar logic here, K times AB equals K A times B equal to K times AB, which is equal to A times KB, because it's a scalar multiplications. It can multiply any matrix directly, no issues in that. And similarly, A times BC is equal to AB times C. It is associative. Matrix multiplication is associative always. And this is addition and multiplication. Addition and multiplication. So A plus B times C equal to AC plus BC. That is also exists always. Even this also exists always. Whenever here is addition, here this is addition, this is a product. So whenever these two are available, then such properties are known as the distributive laws. Parallel processing not necessary here. Transposition means changing the rows as columns and columns as rows. For example, a matrix Aij, A equals to Aij of size m by n, then A transpose denoted by A prime, or maybe the disease pen issues here. Transpose. So A bar A transpose, we'll study it as A transpose. Earlier we wrote here this Aij, and the transpose is like this. And if you transpose it twice, then it will get the original matrix. Means even number of transpositions will give the original matrix, odd number of the transposition will give the different matrix. Suppose even if you transpose the matrix, if there is no change in the matrix, then such a matrix is known as symmetric matrix. So these are some basic properties to be followed. So A transpose whole transpose is A, B whole transpose equal to A transpose plus B transpose. Arbitrary constant times transpose. Since this transpose means that affect only matrix but not to the number. So this arbitrary constant doesn't affect with that. AB whole transpose is B transpose times A transpose. Some special matrices. As we discussed, the symmetric matrix. Symmetric matrix means even if you transpose the matrix, if there is no change, then it is known as a symmetric matrix. A skew symmetric matrix means if you change the if you transpose the matrix, then we may get a negative sign difference. Such matrix is known as skew symmetric matrix. And very easily we may construct the symmetric matrix. So if A is 1, 2, 3, directly write down 2, 3, 4, 5, write down 4, 5, 6. So it is a 3 by 3 matrix. If you want, you can check it out. First row is 1, 2, 3, first column is 1, 2, 3. Second row is 2, 4, 5, second column is 2, 4, 5. Third row is 3, 5, 6, third column is 3, 5, 6. If we transpose this, there might not be any change in that. Suppose the same, if you want to write it as a skew symmetric matrix, let it be B, 1, 2, 3, then minus 2, minus 3, 0, 4, 0, 4. and here -4, -5. Now if you see this, can I write that like earlier logic? No, because it makes a sense that if you take the minus is common, it may not. So the only the condition is here. Let me write down that here. If Aij equals to Aji, then it is a symmetric matrix. Aij equal to minus Aji, then it is skew symmetric matrix. And here I'm going to try here Aii equal to minus Aii. This is in the case of skew symmetric matrix. With that, what I may develop is Aii plus A, 2Aii equal to 0. That makes here Aii equal to 0 means for a skew symmetric matrix, principal diagonal elements are always 0. Now you may get it. For a skew symmetric matrix, principal diagonal elements are always 0. Then only we may construct that. Let me clear the annotations. Then we may clearly see that. Yeah. So A transpose is equals to A transpose, then it is called a symmetric matrix. A transpose equal to minus A, then it is called a skew symmetric matrix. These are some examples. See this. For a skew symmetric matrix, the principal diagonal elements are always 0. And another kind of the triangle matrix, this we are going to use in finding the rank. Especially we are using very badly that upper triangular matrix. So in the upper triangular matrix, number of non-zero rows, number of non-zero linear independent rows are nothing but a rank of that particular matrix. If it is a lower triangular matrix, then in that case also, number of non-zero columns of the lower triangular matrix is also considered as rank of the matrix. Okay, see this. So if Aij is equals to upper triangular matrix means elements below the principal diagonal should be 0. So here this is 2 by 2 only. This is, yeah, there is no element below the principal diagonal, so that's it. Here the principal diagonal elements are 1, 3 and 6. Elements below the principal diagonal is 1. Here principal diagonal element 1, below the 1 are 0, below the 3 are 0, no element is there, so that's the reason. Similarly, if the elements beside the principal diagonal are 0, then it is known as lower triangular matrix. See here, the question is, I'm talking about only the below and beside the principal diagonal element, there should be 0. It doesn't make a sense that here the rest of the elements non-zero. It doesn't mean that. In this, I mean to say that some of the elements are also 0 in that. See, this is the best example for that. This is a 4 by 4 matrix. And one more thing, symmetric matrix and skew symmetric matrix are always a square matrices. A diagonal matrix. A diagonal matrix which consists of only the principal diagonal positions. So these are only principal diagonal elements and the rest of the elements are zeros. It doesn't mean that a principal diagonal is non-zero. It doesn't mean that. It means only here the principal diagonal. Suppose A is a 3 by 3. Then A11 0 0 0 0, A22 0 0, A33. So other than the principal diagonal elements, all the other elements must be 0. That is the meaning of that. And here, this A11, A22, A33 may or may not be a 0. That's the meaning of that. And another matrix is best example in that one, multiplicative identity I, which is suppose if it is a 2 by 2, 1 0 0 1. If it is a 3 by 3, 1 0 0 0 1 0 0 0 1, which consists of only principal diagonal elements. If it is a 4 by 4, 1 0 0 0 0 1 0 0 0 0 0, sorry, 1 0 0 0 0 1. Like this, we may construct the multiplicative identity matrix or unit matrix. The why it's called unit matrix means the non-zero elements are only ones. That makes the sense here. Now coming to the rank of the matrix.